But I know even emails from me. I'm still getting lots of reports of students that are sick, and I even have a student that her whole family is sick, and she was kind of caught without, like, I don't have any way of getting groceries, so I was kind of scrambling to see. I think I have to email her back and see if she's okay. But like, I mean, honestly, just plan on getting sick. Actually, I prepped one, like, ever since of March of last year. I actually prepped to get COVID, and I have not gotten COVID yet, but I stockpiled, like, Gatorade, like powdered Gatorade, and like cough drops, and things like that could be used as cough drops, like Jolly Ranchers, kind of thing. And so and actually I'm hurricane prepared. So I mean, being hurricane prepared is similar to being COVID prepared. So I recommend that you have in general, because we live in where we live in, you should have a 2 week supply of food and other things. But I mean, if you don't, just prepare as if you're going to get COVID, and like make sure you have enough things like medicines, or like I don't know if anyone in our class has kids. I don't have kids either, but like diapers and stuff like that. Like things that would be difficult to live without for 10 days or 2 weeks. So, but how are we doing? Anybody have any questions about anything before we start? And sorry for the gloom and doom. Although the caseloads are a little lower today, that's nice. So, anyways, so we're in chapter 12 and dealing with intermolecular forces, and this is now we're going to talk about some of the so what's when you comes to intermolecular forces. And I aforementioned that states of matter are directly a cause of intermolecular forces. Strong intermolecular forces result in solids, or solids that stick around for a while, and weaker forces, or if the kinetic energy, the kinetic energy is high enough to break forces, you have vapor phase. So imagine, though, we have a vapor. So, vapor where things are moving to, like two water molecules. So a solid stays still, liquid, it's kind of hanging around. Vapor, there's just not enough attraction for the particles to stay together. Imagine you have a gas, though. You have a gas that's just under so much pressure. So you have the water that's flying around, but you put on so much pressure that the water is just kind of stuck, hanging around together. You put so much pressure on it that the gas particles get close enough, and you have this state that's almost like a liquid in terms of the intermolecular, interatomic distances. So that's a specific case, and we call that a critical point. So, and we call that pressure the critical pressure. So, and when you have things that are beyond the critical point, certain rules of solubility break down. So you can get things that dissolve in water that you normally can't beyond the critical point. Same thing with carbon dioxide. So you can use carbon dioxide, for instance, to take caffeine out of coffee. So that's a common way to get rid of caffeine in coffee and coffee beans, is to put it past the critical point for carbon dioxide and water. They do that with the water too. It's like, I think it's this, I don't drink coffee, so I don't know. I think it's called the Swiss water method or something like that. But you get these specific phases. So, and same thing with temperature. So there's a critical temperature and a critical pressure, and kind of beyond this specific temperature and pressure, the idea of a liquid just doesn't make any sense, even though the pressure is so high. Like if you look at the center of the sun, like in the core of the sun, the density is greater than that of lead. It's really, really dense in the center of the sun, just from all the gravity. But what do you call the sun, though? Is it a gas? Is it a plasma? I mean, plasma for this class is kind of the same thing. It's just so much pressure, and there's so much, the matter is so dense. It just, some of these rules, these terrestrial rules, what terrestrial mean Earth, right? I mean, it makes sense, like cell phone is a solid. water, this is a liquid, air, air, it's a gas, no question about that, kind of thing. But then when you start having like really high pressure and really high temperatures, some of these rules of the states of matter that we talk about in general start to break down. And this is one of them. And okay, let me move on though and talk about heating diagrams, heating curve. So right here, if you look at this chart, this is a heating curve. So meaning if you look at the y-axis is temperature. So start at low temperature and go up in the axis high temperature. And then the x-axis is the amount of heat added. So imagine, is that Nikola Tesla? Cool. Someone changed the background. I didn't know Nikola Tesla was in this class. You're welcome, Mr. Tesla. Anyways, sorry. So we have this heating diagram here. So imagine if you take an ice cube out of your freezer. So if you have an ice cube out of your freezer, and that's going to be down here. So down here in the bottom corner. So you take an ice cube out of the freezer and then you stick it on your stovetop and you turn on the heat. So it's kind of the heat in this direction is just the heat is added. And what happens now initially, so you have this ice cube, as it's heating up, you start off at negative 25 degrees Celsius. So it's a cold ice cube. And then it heats up and it gets to 0 degrees Celsius. And then after 0 degrees Celsius, the ice cube starts to melt. So it's melting here. And in this state 2, you're gonna have a mixture of solid and liquid. And then you get to stage 3, where it's all water. So it's all liquid water. And then it just heats up. It's just liquid water, higher temperature. Then you get to point 4, where the liquid starts to boil. So you have a combination of liquid and vapor. And then you get to point 5, where you end up, it's all vapor and you heat it up, and that's known as superheated steam or dry steam. So a couple things about these states and notice a few things. So during the phase changes, notably 4 and 2, the temperature doesn't change. So the temperature doesn't change. And that's because we talked about this last class, it's a dynamic equilibrium. So actually you have in the melting phase, well, not phase, melting region, you have both solid being formed and solid turning to liquid. And it's an equilibrium, although over time with the added heat, it turns out to melt more than it freezes. Same thing when things are freezing, it's going to go back and forth between liquid and solid. But as it's cooling down, eventually the solid overtakes it. So then just colloquially, so steam here at that point, and also as it's coming off of this point, this is known as saturated steam, or also like colloquially as wet steam. And at point 5, scientific name for this is superheated steam, also known as dry steam colloquially. So dry steam or superheated steam is very dangerous. So wet steam or saturated steam, I've never seen superheated steam. I've only seen saturated steam. So because it's called saturated steam or wet steam, because if the steam hits you, it condenses and you get wet, right? So if you go to the steam room at the weight room or the gym, I like going to the steam room. I think it's great. You walk in there, the steam condenses. I turn like beet red like a lobster, and then I'm covered in condensed water, right? So that's wet steam. I get wet that way. And the thing with superheated steam or dry steam is, so this is typically used in power plants and also in naval vessels. So when you use steam to turn a steam turbine, so you use superheated steam to turn a turbine's like a fan. And so you have really hot steam come in, it turns the fan, and you have cooler steam coming off. And you make it superheated because you don't want the steam to condense along the turbine, because it makes the turbine corrode. It also puts weight on it, which can cause it to degrade over time. So you use superheated steam. Problem is, if one of those steam lines rupture, the superheated steam comes out, and it can it's been known just to take pieces off of people. because it's really hot and it just vaporizes whatever kind of comes in contact with it. So that's I mean, like if you're on a Navy vessel and it gets hit by a torpedo in the engine room, and the mechanics in there can get really injured from those things. And also power plant, same idea. So and although you probably won't get hit by a torpedo in a power plant, more like an earthquake or a fire or something like that. So okay, but a couple things. Well, let's talk about the thermodynamics when you're doing the problems. When you do the problems for these, in states number 1, 3, and 5, you use the equation Q, the heat, is equal to the mass, the specific heat, times the change in temperature. And for this case, the mass is all going to be the same, but the specific heat changes for each phase. So depending on what phase you're at, the specific heat changes, and then change in temperature. So just how much temperature you are, because this one in this diagram, it goes from -25 to 125 Celsius. So pay attention to where the temperature is changing there. Then during the phase changes, so 0.2 and 0.4, so to calculate the heat or energy in this stage, the heat is equal to the enthalpy, the enthalpy of fusion for melting and or freezing. So the heat of fusion times the number of moles, N is the number of moles. And then for vaporization, it's going to be the heat of vaporization. Or if it's condensation the other way. So condensation the other way, it comes down. Someone's microphone is on. I'm gonna. I don't know. Let me find out. There we go. Okay. So, if you want to talk, you can always unmute yourself if I've muted you. So, what was I talking about? Oh, and if you have sublimation, we'll talk about phase diagrams soon. Sublimation, that's when you have solid going directly to vapor. The heat of sublimation is just the heat of vaporization plus the heat of fusion. So that works for all cases. So that's true for all cases. So how are we doing some more questions? Just so you know, a couple things. This chart is not entirely accurate. How most charts look, so temperature and heat, so things, at least the melting curve, the bottom part, it usually looks like this. So I'm trying to draw this so that there's actually a slight incline in that. And I'm also showing you there's these regions here. So most solids, solids are typically amorphous. So if it was a perfect crystal, so if this diagram was, if we were doing the melting point of a single crystal, perfect single crystal, it would look exactly like this. But if you look at this ice cube here, this is obviously not a perfect crystal. You can see it's got regions of white, it's just different colorations. And as you heat this up, the areas that are under higher stress, they're going to melt first. So you can see, I mean, there's just little dots here. Those are going to melt first, and they're going to melt at a slightly lower temperature. And then there's also going to be some regions that are particularly stable, and it's not going to be as pronounced as the ones in this region, but there are going to be some up there that are just gonna melt last. But in general, the higher stress ones are gonna melt first. And so because of that, your heating curve is not gonna be that. It's not gonna be the one in red. It's actually gonna be a slight curve. Likewise, in a cooling curve, so a cooling curve will typically look like this. So temperature's going down, and you can get something that looks like this. And you have this region here. This is known as a super cooled liquid. So when you cool things down, you can get what's something called a metastable. So meta means sorta stable. A super cooled liquid. What is a super cooled liquid? It's a liquid that's slightly below its freezing point. And so these are they're unstable, meaning it's not going to explode unstable, but it's just they don't typically last very long. And it's a lot of fun. If you ever get super cooled liquids, I like doing that because I like to make slushies. You know, like I'll take something like Gatorade or vitamin water and I'll stick it in my freezer. And if it always goes into a super cooled state, and it's kind of fun to take it out and I just take the bottle and I whack it and it freezes immediately. It's really cool. Or it turns, it turns to slush. Depends on where you're at. If you get it perfectly, you hit it, it's going to turn into a big solid block of ice. But I mean, I haven't gotten to that perfect state yet. It's always turned to slush, but it's fun. And I also like it because I like to eat the slushy because it's more uniform. Because if you let it sit for a while, then the same thing happens where the liquid starts to freeze at different temperatures. Well, because it's a mixture. This is a pure substance. If it's a mixture, it's gonna look something like this, where it curves down a little bit more because of things like the sugar and whatnot in it. It's gonna have. We'll talk about this 2 chapters. The melting point depression. You're going to have the different mixtures freeze at different temperatures. It becomes ununiform. So I that's my favorite is the super cold liquid turn into a slushy because it's cool to watch and then it's pretty uniform in terms of its product. But yeah, that's if you ever heard of super cold liquid, that's what it's at, and this is where it fits in the diagram. But that's more of an exotic state. I mean, generally speaking, you're not going to see that as much. Especially looking over long time scales, the super cooled liquid doesn't matter. It's just going to go away. So how we square? Any questions? All right, so here is a phase diagram. So, and this is specifically for water. And looking at this, and you can see it's not drawn to scale. The y-axis here is pressure, and the x-axis is temperature. And so a couple things to note. So we have 3 phases. We have solid, liquid, and gas, the 3 phases that matter there. At least we talk about in this class. I know there's more. You can argue plasma, you can argue something like Bose-Einstein condensate, but no, I mean, we're not going to talk about those other ones. We're going to talk about simple, solid, liquid, gas. And you can look at a couple things. So first of all, I'm going to draw a line. And so this line here, this is known as an isobar. So iso means same, bar for like barometric pressure. So isobar means same pressure. This is all at 1 atmosphere pressure, 760 torr. So if you start off at absolute 0 or something really cold, you at one atmosphere pressure, water is a solid. And as you heat up the water, so isobar, same pressure, temperature increases, you get to 0 degrees Celsius. And in this state, you have the solid freeze. I'm sorry, melt, excuse me. I saw freeze. You have the solid melt. So going from solid to liquid, that is known as melting. And then going from liquid to solid, that's known as freezing. So that falls along that line there, and that line being this line here. So now you have liquid water, and it continues on. and you get to this point here. That's known as the boiling points. The boiling points. And so, of course, going from liquid to vapor, that's known as boiling. Going from vapor to liquid, that is known as condensation. So, and then you have the gas phase, and then this is going to be your superheated dry steam there. Okay, so that's an isobar. Now let me draw another one. I'm going to draw an isotherm. So that vertical line there, this is an isotherm, same temperature. So this isotherm at low pressure, same temperature, very low pressure, we have the vapor phase. It's a gas, and as as the pressure increases, you can get water to liquefy by increasing the pressure. So actually the other way around, when you go and you draw a vacuum, this is typically done. Have you wondered how we get like stuff like instant coffee? I also told you I don't drink coffee, so I mean, I don't know the flavor difference. The way that you make instant coffee is you make coffee and then you draw a vacuum and all the water boils off, and then you're left with all the powdered coffee. So if you ever wondered how you make instant stuff, that's typically how it's done, is actually by drawing a vacuum. So, and I also didn't mention, okay, so here's your isotherm. Where the solid melts and freezes, this is known as the fusion curve. And where the liquid boils and condenses, that's known as the vaporization curve on a phase diagram. I mentioned, so we have the liquid phase here. Below this, we have the sublimation curve. And this is when the pressure is too low that a liquid phase can't form. And the going from solid to gas, that is known as sublimation. And going from gas to solid, that is known as deposition. So if you ever wondered something like do you ever have like old meat in your freezer, or like I've seen this, I do this all the time. Someday I'm like, you know what, I want to buy some frozen peas, and I go to Costco and I buy this huge bag of frozen peas, and it takes me like 2 years to go through that bag of frozen peas. And whenever I want to have peas, I have like this snowball with like shriveled peas. So of course, when I first buy it, it's all frozen peas. It looks proper. And then after a year, I get like, snowball with shriveled peas. What is actually going on in your freezer is the ice. The ice is subliming to vapor, and then it's depositing back down into ice. So that's, if you ever wondered why freezer burn happens, it's actually because of that equilibrium and phase transfer or phase whatever change going on in your freezer. Okay, so another point I want to mention is the triple point. The triple point right here. And the triple points, so we're kind of used to seeing the phases of water. Water, I mentioned, is a weird substance, and we're actually pretty comfortable seeing water in all three phases. It doesn't bother us like, oh, it's ice, it's water, it's steam. I've seen all three of those. How many of you have seen vaporized aluminum? I've only seen solid aluminum. I have not seen liquid aluminum, and I have not seen aluminum vapor, right? So aluminum to me is a solid metal, right? But water, like, oh, we're cool with all three phases. And we're also familiar with the phase changes. So meaning that when we see freezing or melting water, we're fine with the fact that and it makes sense. Like, oh yeah, I have ice in my drink and the ice is slowly melting away. It's actually, I see we have solid and we have liquid at the same place. That's fine. So, and also when we're boiling something. So when we're boiling something here along the vaporization curve, we have water vapor, bubbles, gas, and liquid water. That's fine. But you can get to something called the triple point, and where you have the triple point, you actually have all three phases. So for a triple point of water, you're going to have solid ice in boiling liquid. I've only seen it for carbon dioxide. I've never seen it for water. The pressure is too low for water. Carbon dioxide, it's around 5 atmospheres. You can get to the triple point, and it's pretty interesting to see. So carbon dioxide liquid is clear, and dry ice, solid carbon dioxide, is white, and most things sink, and the solids sink in the liquid. So if you imagine clear liquid with solid white carbon dioxide in the bottom with bubbles coming up, that's what the triple point of carbon dioxide looks like. It's really, really funky. And but the triple point is where you have all three phases of matter, or at least being solid, liquid, gas, in equilibrium. And so there you have it. And water is weird. Most other substances, this is what the curve looks like. So water is weird such that the common solid is less dense than the liquid. There are solid forms of water that are more dense than liquid water, but the most common one, at least at this pressure and temperature, or temperature range, I should say, this pressure and temperature range is less dense than the liquid, and that's really, really weird. So, and because of that, one of the ways you can melt ice is to put it under extreme pressure, but it has to be extreme. So it used to be thought that ice, like ice skating and stuff like that. So I mean, you can skate on ice, but you really can't skate on carbon dioxide like dry ice. Well, dry ice can be fun because it sublimes, and it's like I in grad school we used to play air hockey with it. Like on Fridays we would take some of the carbon dioxide and take chunks of it, and like if you have like a hockey stick, you can hit it and it'll spin, and go on the ground because it has that vapor on the bottom. So it's kind of fun to play hockey with carbon dioxide. Just don't pick it up with your hands; it'll freeze, of course, But you can play, like I said, like kind of a poor man's skeet ball or something like that, or whatever it is with chunks of carbon dioxide. But anyways, water, and I know we live in the tropics, but everywhere else it's winter, and it's winter here too, but you can ice skate. It's one of the things you can go ice skating. And it used to be thought that that ice skating worked by the fact that the pressure from the skate melted the water, the ice. So, but that's not the case. It turned out to be false. What's really going on is that the ice is slippery. The reason why ice is slippery is because it has liquid at the surface, and depending on the temperature, that liquid layer grows or shrinks. So close to freezing, it's a relatively thick liquid layer, and if it gets cold enough, ice is just not slippery. And I used to live in Wisconsin, and I can tell you that ice doesn't have to be slippery. So once it gets to be really cold, and I mean like negatives, below zero, ice is not slippery. And it's hard as a rock too. You slip on, I mean, you can still slip on snow and whatnot, but I mean, if you fall on ice, it hurts. And also, like I said, it won't be slippery. I mean, oh man, I was talking about the snow days that in Wisconsin, they only closed the schools when the wind chill was like -60 Fahrenheit. Oh, and you could stay inside anyways. But yeah, under that temperature, there is no liquid layer on water. It's just solid. Whereas close to freezing, ice is pretty slippery. So that's got to do with the liquid layer. That's not in the textbook. That's only recently. Okay, and as promised, so also not to scale. Here's water. Water has same idea. Y-axis is pressure, x-axis is temperature, and we have different forms of ice. So ice one, sometimes called alpha ice, I've only seen that kind of ice. I've never seen these other types of ice before. But if there's enough pressure, you can form these other types of ice. And so we actually do see these other forms of ice in various places. One of them is at the bottom of the ocean. So, I mean, 4 miles or so of water, that's a lot of pressure, putting down, you can form some of these different forms of ice. Also in underneath certain permafrost, like in Siberia. And specifically with these ices, you can get something called methane hydrates, where you get methane trapped into these exotic, and I'm saying exotic because it's not the common kind of ice that we're familiar with. Methane hydrates, it's methane trapped in these different forms of ice. So if you ever heard of the word methane hydrate, now you know it's ice that has methane trapped in it. And methane hydrate is interesting because it's an ice cube that burns. So if you take methane hydrate and you light it on fire, it'll actually burn. It'll release the methane, it'll catch on fire, and it'll melt the water, melt the ice, releasing more methane as it goes. So, and this is a problem in Siberia specifically, because when it comes to building things, like say, we typically don't have basements here, right? But a very common way to form a basement, especially in bedrock, is to use explosives and blow out the bottom, or also make building roads. Like, oh, there's a hill in the way. What do we do? I know, let's blow it up. That's a very common thing, and then we do that here on Maui too, right? I mean, when we build roads, we blow up the hills. So it's very, very common. And problem in Russia is when they do that, sometimes they get a bigger explosion than they intended. And that's because they'll hit methane hydrates and just causes a massive explosion. So be very careful if you find yourself being a demolition expert in Russia or Siberia, which is part of Russia, right? So because it's a dangerous job. But okay, so if you're methane hydrates, now you know what that is. So let's look at other diagrams and compare it to water. Right away, so on the left here is iodine, and the right here is carbon dioxide. And if you remember, water had the liquid, the fusion curve pointing backwards. These other ones have the fusion curve pointed forward, has a positive slope instead of a negative slope, right? So that's more common for water is a weird one that has a negative slope. Whereas by the slope, I mean the y equals mx plus b. So, right, the positive slope means this direction, negative slope means the other direction. So that positive slope is the most common thing for the fusion curve for other materials. Same idea, y-axis is pressure, x-axis is temperature, and you'll see a few things. So for iodine, you do have a triple point, and iodine mostly looks like it sublimes. You actually can get to liquefy, but it doesn't really show up as much. But we most commonly see iodine either solid or vapor. And same thing with carbon dioxide. And I told you the triple points are on 5 atmospheres. We're used to seeing carbon dioxide at this pressure sublime. So sublime means solid directly to gas. So that's the more common ones. So, and I mentioned this before. Last thing I'll talk about, water is a very strange substance. So, I mean, we've mentioned some of these things before. By water is weird. So water is 18 grams per mole, and it's close to methane, 16 grams, and ammonia, 17 grams per mole. Both methane and ammonia are vapors at this temperature, so and pressure. So I mean, the fact that water is a liquid is really weird. So it has really strong intermolecular forces for its mass, and which gives it this long liquid phase, and that is responsible for many of its properties. In water, because it's so strange, we look at it especially for life. So one of our missions right now, their scientific endeavors, we're looking for life outside of the Earth, and we haven't confirmed it yet. We see some things that maybe there might have been life on Mars. We're probably even say there probably was, but we're not really sure. We haven't, and last year it was all about like, oh, we might have life on Venus too, but we're not so sure about that. It's kind of, we're seeing phosphine. It's a chemical. Like, why are we seeing phosphine? Where's it coming from? And we're still kind of wondering. And one of the things though that we really, really look for liquid water, especially when it comes for life. The other thing we're going to look for is oxygen gas, and a lot of oxygen gas. So if you look at the planet Mercury, the atmosphere is about 35% oxygen, but there's no life on Mercury, at least none that we are familiar with. The reason why there's so much oxygen on the atmosphere in Mercury is because it's close to the sun, and the sun just vaporizes the rocks. So the atmosphere is very thin at Mercury. So whereas Earth has a relatively dense atmosphere, not as dense as Venus, not as dense as Titan, but denser than Mars, kind of thing. And we have a lot of oxygen. That oxygen in our atmosphere is from plants, mostly algae, right? So our oxygen is directly from life. So that's going to be one of the things we're going to look for. But anyways, I already mentioned ice is slippery. That's weird. How many solids do you know that are slippery? Water is also an extremely powerful greenhouse gas. So if you look at the different other celestial objects, so Mars has a 60 degrees Celsius difference between day and night. And that's a huge difference, right? And look at the moon. The moon is around 300 degrees Celsius. I mean, so it's really hot. It's both hot and cold. So it's both hot and cold on the moon. During the daytime, it's really hot, and nighttime, it's really cold. And so if you're familiar with the James Webb Space Telescope, so the James Webb Space Telescope is going to be about the same distance to the sun as the Earth, but it's going to an area called the Lagrange point. And the Lagrange point, that's sort of a stable gravitational point where the sun and the Earth and the third object, in this case a satellite, is relatively stable. And so the satellite's going there, and it's an infrared satellite, so it's going to have a heat shield pointing at the sun at all times. So it's going to be pretty cold, and they need to be cold. So the detectors are always going to be away from the sun. So, but I like the Space Webb Telescope. That's an interesting instrument that they're sending up. It'll be neat to see the data from that. So, and water is really the greenhouse gas for the Earth. I know we talk a lot about carbon dioxide, but carbon dioxide does not have a very significant impact on the greenhouse effect for the Earth. And the greenhouse effect of the Earth is pretty significant as well, because without it, our average temperature would be about negative 15-ish degrees Celsius. And the average temperature of the Earth is around 15 degrees Celsius. So we have about a 30 degrees greenhouse effect, 30 degrees Celsius greenhouse effect. And without that, I mean, life would be very different. The climate of Earth would be very different without the greenhouse effect. And if you to give you an idea how water changes some of the greenhouse effect, if you've been to the desert, so if you've ever been to a desert, like Las Vegas is in a desert, and it's really hot during the day and it's really cold at night. And why is it that way? Because there's not very much water. I mean, there's still water in the air in a desert. It's just like 15% or 10% humidity. So there's still water. But if you go somewhere like Antarctica is the worst desert in the planet. And you think it's weird that Antarctica is a desert, but there's just no water in the atmosphere over Antarctica. The air is very, very dry. And Antarctica is really cold at nighttime, because it just doesn't have the water there to trap in the heat. And also, if you study climate change, there's something called climate forcing. So carbon dioxide is a relatively weak greenhouse gas, but the idea is that the carbon dioxide emissions cause more water to evaporate, and that causes climate forcing. So really the culprit for global warming is water. But it's carbon dioxide is causing more water to evaporate. So what else is weird about water? Water has a pretty high heat capacity. It doesn't have the highest heat capacity, but it just has a high heat capacity. If you remember, we're doing the calculations, and water is like 44 kilojoules per mole. The latent heat is 44 kilojoules per mole, and acetone was 30. So because of all this intermolecular forces, it can store, it stores a lot of energy. One of that is high heat capacity. And why does it have a high heat capacity? So we haven't talked about it too much, but water is a V-shaped molecule. So you can store energy in certain ways. So temperature is one. This is temperature. It's translational energy. Water can also store things rotationally. This is rotational energy. And then there's vibrational energy. So because of its structure, water can store energy rotationally and vibrationally, and alongside with temperature. And then because of that, it takes a significantly more amount of energy to raise the temperature. And also, as water is cooling, it releases a significant more amount of energy as it's cooling. So, but I said before, it's not the highest heat capacity. Ethylene glycol, what's commonly used in antifreeze, has a higher heat capacity than water. So water's not like the biggest ever. It's big for its size. So again, and ethylene glycol is a bigger molecule than water. So it's not surprising that it has a higher heat capacity. Water has a very high heat capacity for its size. And the other thing with water, ethylene glycol having a higher heat capacity, that's another reason why we don't have specialized cars for like Hawaii and California, or at least the coast or coastal United States or Florida kind of stuff. I mean, it never freezes here, right? Unless you, in the odd day on Haleakala or very infrequently in Mauna Kea, but like, who's going to go up there other than astronomers, right? Or religious specific folks or hikers or other people going up there. People very infrequently go to places in Hawaii where it freezes, and if it freezes, they're going to stay away. So why do we have cars that then don't just have water in them? Like, why do we need antifreeze? And the reason is because of the heat capacity of ethylene glycol. And then we have a smaller radiator. If you had water, you have a bigger radiator. So if you're wondering why, and the other thing is the cost of production, because then you'd have to have two different types of cars on the road. One that could never be in a cold climate, and another one that could be fun in a cold climate. So, I mean, okay, thing. Water is also, it's a great solvent, especially for ionic compounds. So great solvent, and it transports nutrients and toxins very well. And this goes back to the environment. So water is a good source of nutrients on our own bodies, right? Our bloodstream carries nutrients, not just oxygen and our hemoglobin, but it carries other nutrients too. Carries sugars, carries vitamin C, lots of things in our body, and it also transports toxins. So if you were to eat something that's toxic, or it can dissolve in your bloodstream as well, and can carry those toxins out to your body. And same thing with things like waterways. So if you start dumping things in rivers, then the rivers can carry the toxins, nutrients, and toxins. And actually, dumping nutrients in the river is a bad idea too, because you can get something called eutrophication, where you have algal blooms from nutrients that just appear. And those can also be very dangerous. You see that quite a bit on Oahu. It's more frequent on Oahu. If you, especially in Kaneohe Bay, you'll have some of the nutrients from wastewater, the phosphates, tend to have algae growing on the reef there in Kaneohe Bay. So there's quite a bit of research done on that. And also, aforementioned that water, the common solid near STP, standard temperature and pressure, it's less dense than liquid. That's weird. That is really weird. So anyways, there's my water is strange lecture. Anybody have any questions? And I don't want to rate notability. I want to use it. Okay, so I'm going to move on and talk about chapter 13. I think we'll get through this today as well. But there's only a few concepts to talk about. One of them is packing. So let me talk about simple cubics first. So this is something called a unit cell. And we tend to use quite a bit. We tend to use Cartesian coordinates. That's from Rene Descartes, the guy that I think, therefore I am, if you've studied philosophy. That's Rene Descartes. That is the X, Y, Z axis, or Z, I guess, if you're in Canada or England. But so if you're familiar with graphene, so like graphene making graphs, this was from Rene Descartes. And legend has it, he was watching in his window panes, he was watching raindrops go down from his window panes, and then he thought, oh, that's how I can graph a line. So that's how legend has it. I don't know if that's true or not, but that's Rene Descartes, hence the term Cartesian coordinates. And we frequently, with our mathematics, we use a lot of Cartesian coordinates. And atoms are spheres, or mostly close to sphere-like, and they're they arrange as in spheres in space. But because of our math, we like to think of things in Cartesian coordinates, X, Y, Z. So we make cubes. So we'll make our cubes, and there are different, and things pack in different ways, and some very common packing ways. One of them is the simple cubic. So sodium chloride salt, for instance, has a simple cubic, and this is just atoms stacked up on top of each other. And like I said, it's a simple cube. And if you draw a cube, so if you look at this, if you have that, you can draw a cube in the middle, and you don't have any atom in the middle. You just have each corner of the cube has an atom, the center of each of these atoms is one of the corners of the cube. And if you think about boxes, right? So if I have boxes, I can stack 4 boxes on the bottom, and then you can, on top of those boxes, you can stack 4 boxes on top of that. So that means an atom in the center, in each of these boxes, each of the atom has about 1/8 of its volume in the if you have 8 boxes, I should say about, it's exactly 1/8 of its volume is on those 8 stacked boxes. So each corner then is 1/8. And how many corners does a cube have? Cube has 8 corners. Each of them has 1/8 of an atom. So a simple cubic, the unit cell in a simple cubic, has the equivalent of an atom in it. And so this actually has a pretty large amount of free space. So only 52% of the volume is being occupied by atoms. I know that the electron cloud of the atoms is. So simple cubic's not a very good packing efficiency. And here's some other equations. The edge of this, so this edge right here is 2 times the radius of the sphere of the atom for a simple cubic. And then you have body-centered cubic. Body-centered cubic is the same thing as a simple cubic, except there's an atom in the center. So if you take your simple cubic and you put an atom in the center, you get body-centered cubic. So and the packing efficiency is twice as much as, it fits twice as many atoms in the unit cell. So you still have the 8 corners and 1/8 for each of the corner, and you have the whole atom in the center, and that equals 2. So you have 2 atoms in the unit cell for a body-centered cubic. And then in terms of the radius, the edge and the radiance, there you go. That's done with trigonometry. And then you can see the packing efficiency is slightly higher. And then you have face-centered cubic is another common one. Face-centered cubic is where body-centered cubic, you have an atom in the center. The face-centered cubic, you have atoms all along the 6 faces. So a cube has 8 corners, but it has 6 faces. you have atoms along the 6 faces of the cube. And if you have an atom on the face and you have 2 boxes and an atom in the center, that atom is sliced in half. So you have 6 atoms sliced in half plus the 8 with the corner. That's 4 atoms in the unit cell. So 4 atoms in the unit cell for face-centered cubics. And a really kind of interesting application for this is summarized like a katana blade. And it's interesting the way this works. So steel, usually when you say steel, if you don't mention someone like stainless steel, you say, oh, it's made of steel. Usually what you mean is carbon steel. Carbon steel is about 2% carbon and 98% iron. So if you have an I-beam and like most of like, we have iron nails, but they're not iron, they're steel. So if you go and you buy something that's made of iron, we almost even say it's, iron. We don't usually say iron. It's usually steel. Well, I shouldn't say, we do say iron, but it's typically not iron. It's typically steel. And it's 2%, it's carbon steel, 2% carbon, 98% carbon, 98% iron. And what we found out though, and this is technology as old as the Roman Empire, that if you add a little bit of carbon and you heat the heck out of iron, you get a really powerful metal. And it's very hard to break. And steel was very, very coveted. In fact, some scholars, if you heard the sword Excalibur from King Arthur, they thought that the magic steel, they thought of magic swords being because some of the Vikings figured out how to really heat up iron and could make high enough temperature to make steel. And they think that maybe that the idea of the myth of Excalibur and these magic swords came from the fact that we had these steel swords and they were hard to break. And they thought like, oh, it's a magic sword, because iron is a little more brittle. If you're a soldier and you're whacking at another person's armor or iron sword, the sword can snap. So that's a possibility. But let's go back to the Japanese. The Japanese figured out that they figured out also the carbon steel, 98% iron, 2% carbon. And, but there's also iron carbide. Iron carbide is 10% carbon, 90% iron. And iron carbide is very brittle. It's an ionic compound. So, but it's also very high in terms of shock and heat. So horseshoes, for instance, are made from iron carbide, and certain engine parts are made from either nitrided steel or cheaper iron carbide, depending on how cheap your manufacturer is. So iron carbide is very tough. It's a very tough material, but it's also brittle. But what the Japanese artisans found out is that you can put iron carbide ribs along the sword, and if the sword is carbon steel and you put these ribs of iron carbide along them, you get a very powerful sword where it has the combined tensile strength of the carbon steel and has the durability of the iron carbide. And I guess with these swords, they can slice through people and various things. They're very formidable weapons, at least in terms of melee weapons, right? I mean, I given the choice, I'd rather have a machine gun than a katana blade, but depends on, I guess, on the time period. And it's a combination from that. Okay, but let's go back to carbon steel. So how carbon steel works, and iron is an interesting. Well, I studied iron in grad school. I worked on single crystals of iron for part of my PhD research. And iron, it goes from, so iron below 900 degrees Celsius is at face-centered cubic. But if you increase iron to 900 degrees Celsius, it becomes body center cubic. So iron actually has like this around 900 degrees Celsius. It expands. The atomic structure, the metal structure of it changes. And what you can do is if you have iron and if you put a little bit of carbon into it to form this carbon steel, but the next step is you quench it, you throw it in water. And if you ever see movies where they're making swords, one of the things they always do is they'll take your iron ore and they'll put it in the fire, and then they'll start whacking at it, and there's sparks flying everywhere. That's releasing something called slag. It's usually calcium magnesium silicates. It's impurities. You're whacking at, you're getting rid of slag. If you melt it completely, the slag floats on the top. But for the old fashioned blacksmiths, you're whacking at the thing, sparks are flying everywhere. That's your slag coming out. And then you stick it back in the fire, you whack it, and then occasionally you throw it in water. Why are you throwing it in water? Especially at the end, especially when you're completely done, you quench it in water. And the reason why you do that is because the structure goes from body center cubic right back down to face center cubic. And if you have the structure, so I'm trying, if you can see this, they have kind of blue iron. And if you have these black carbon atoms, and if you quench it real fast, it shrinks the structure really quickly, and you get that carbon stuck in there. And why is steel better than iron in terms of its strength? It's because it holds the iron in place. So if you look here, so here, that's iron metal. It's going to have a metallic bond, so meaning you have the electrons flow freely. This is still going to conduct electricity. It's going to flow freely. But now, if you put a big force, so if you shock it with a big force, and metals are ductile, which means they're bendy. They tend to deform. But carbon steel, if you have a carbon atom there, it's going to push back. It pushes back and saying, you know what, iron, I'm going to give a force pushing back, and the other carbons push back, and then the steel does not deform. So hence carbon 2%, carbon 98% iron steel is a lot stronger than just plain old pure iron. So if you're wondered how they get steel, and that's also how they make it, but also kind of a cool application with the samurai swords. There's other types of packing. Things can form hexagonal shapes. So platinum, for instance, forms this hexagonal packing. We're going to cover more of the unit cells with the Cartesian coordinates, not hexagonal, in this class. Okay, and I'm talking too much. I'm not going to get through this chapter. That's fine though. Okay. So chapter 13, in the old textbook, the previous editions, this used to be part of chapter 12, but I guess that's the way the textbook companies make money. They switch things around. They charge you another enormous fee for a new edition. The only difference between the 4th and 5th edition, well, I guess they took the chapter 4 and they split it into 2 chapters, and then they took chapter 12. I mean, what was used to be chapter 11 into 2 chapters, but it advanced one. Anyways, this is still with the theme of intermolecular forces, and also things like melting points and boiling points. So let's talk about all things. And and we'll start with solids. And this is crystalline solids. And remember though, amorphous is more random. Everything with a very few examples is going to be amorphous. So if you find a diamond, a diamond is going to be crystalline. So you can find really pure crystalline diamonds. But if you find carbon, generally, if you take some anthracite coal, it's Well, besides the fact it's going to be it'll be graphite, but it's going to be amorphous graphite. It's not going to be crystalline graphite. So even iron is a mixture of different structures. It's not all the same structure, and especially at the surface, it's very different. So, but anyways, and I mentioned that also. You saw the ice cube, right? It's in the previous chapter in the lecture today. You can see there's different crystal structures in there. It's not the same crystal structure going through, and so that's how most things are, as they're amorphous. But all crystalline structures, so they can be molecular solids. So on the left here, so this is molecular solid, meaning it's made of molecules, so stable units of atoms like water. I can be ionic solids where you have ionic bonds like sodium chloride salt, and you can have atomic solids. So where the pure substance in question is made up of only atoms. So for molecular solids, so made of molecules, so these, generally speaking, tend to have low melting points. So these tend to have low melting points. So, and I also, maybe it's confusing, but we just spend all the time, water has a very high freezing point relative to other things, relative to other molecules. So relative to salt, so salt is an ionic compound, and salts have very high melting points. I've never seen molten salt before. I guess I've seen lava. I've seen molten rocks. So I guess I take that back. I have seen molten ionic compounds. I haven't seen molten sodium chloride though. So I've taken, I mean, we've in chem lab and stuff, we've taken with a Bunsen burner and we've heated salt till it turns bright red, but it doesn't melt. So that's pretty hot. So sodium chloride salt has a very high melting point. So relative to molecules, ionic compounds have a very high melting point. Then for atomic solids, so non-bonding. So non-bonding things like noble gases. So things like xenon, argon, and helium. You could even argue helium may not even have a solid state or a liquid state for that matter. So, but these non-bonding ones have very, very low melting points, lower than molecules. So you don't see solid xenon around very long. Metallic bonds, these have variable melting points. So it's really hard to say. And it's not really any rhyme or reason for this. There's no periodic trend in this either. Like you look at the periodic table, right? So let's look at a periodic table, and we're talking about metals and their melting points, right? So here's mercury, and the melting point for mercury is around -40°C, right? So, but then you look at cadmium in the same family. Cadmium's melting point is 320°C, and that's just high in the periodic table. And zinc above that, zinc's 420, right? So these are, zinc and cadmium are clearly solids, and mercury is clearly a liquid. And then if you move over, so right here's gold. Gold's going to be melting points 1,000°C. Then you get the platinum. Just moving over, platinum is at 1770°C. So it's really hot. It's really hard to melt platinum. Actually, platinum, so rings made of platinum are hard to work with. It's hard to make them because, among other things, they're so hot that you can get sunburnt. So you can get sunburnt from them. There's some metals are like that. They're so hot. Magnesium over here, when that burns, it burns so hot it glows in the ultraviolet too. So you can get sunburns from working of these ultraviolet radiation burns. It's not from the sun, but it's a radiation burn from these metals glowing in the ultraviolet. So it can be really dangerous. And I mean, this is a little off topic of sort, but thorium, I always like this. Thorium has a really high melting point, and it's similar to platinum, but thorium was called after the Norse god Thor because of its high melting point. So but next thing we'll talk about are covalent networks. So, and I'll go back, but if you look at some of these elements that have network covalent, so boron is network covalent. Look at its melting point. It's at 2075 degrees Celsius. So this is when you have network covalent, there's a very, very high melting point. So metals, when you have a metallic bond, so there is not really any rhyme or reason here. Like it kind of bugs me as a chemist, right? Because I like to be able to predict things. So, but you like if you look at mercury, that's weird that I mean, like in two elements over platinum, it's like really hard to melt. And then mercury is a liquid, and then you get to thallium, and you get a melting points going back up, right? And then you over here, like generally speaking, the alkalis are low temperature, but cesium is really low, right? I mean, so cesium is a pretty low melting point. Melting point 28 degrees Celsius. So on a warmish day here in Hawaii, that's it's gonna melt that. So there's various like I said, the metals there's just no trend. But network covalence, you can see it's really high. So melting point of a diamond is 3,500 degrees Celsius. So that's really high, right? And silicon. So then that question, and so we get to the metalloids. So what kind of bonding does silicon have? So part of it, silicon does not have metallic bonding if you look at its melting point. So, well, I guess it's medium, but it does not conduct. It's at this temperature, silicon does not conduct, and you can see it's got a relatively high 14 Celsius. Not as high, but it's weird in that way. It's not, I mean, not like carbon. Carbon's, network covalent, really, really high. So I'm going to go back to, come on, notability. All right. Network covalent, these have very, very high. And and certain elements, certain compounds, so quartz, silicon dioxide. And this is one of those weird things where scientists like to fight. So a chemist will tell you that silicon dioxide's formula is SiO2. A geologist will tell you it's SiO4. And the reason is because silicon has oxygen in the tetrahedral spots. But each of these oxygens also have silicon in then tetrahedral spots. So if you go by the chemistry rules, silicon dioxide is SiO2. If you go by the geology rules about connectivity, the structure is SiO4. So depends on, I guess, on whom you ask. But we both geologists and chemists agree that the atomic ratio for quartz is 2 parts oxygen to 1 part silicon. But then the formula structure we argue over, because chemists, we like to think of the atomic number in terms of unit cells, and geologists like to think of the terms of their connectivity. But we're both right, but we have different viewpoints. So, but silicon dioxide, for instance, I should say quartz. I'll get in trouble by any geologist here if I call it silicon dioxide. Quartz is a network covalent molecule. And so what? I got 3 minutes left. I did a project once. I was working for a startup company, and they were looking at a way to make to recycle motor oil, and so they wanted to recycle motor oil into either crack it in diesel fuel or make it into asphalt, or to recycle it to motor oil. And the idea was that they would use this metallic bath of lead bismuth. And lead, generally speaking, when you alloy metals, they tend to, generally speaking, they can go up. They tend to decrease their melting point. So lead bismuth has a pretty low melting point. And the idea was that you would use this entire metal bath as a heat transfer medium, and then you could really you could make a much smaller vessel and put a bunch of motor oil in it, and you'd have a smaller vessel, less energy, and then have a huge throughput for your recycling center for motor oil. And they found that there were these tiny spheres forming that, and they couldn't quite figure out what they were. And what I did is I found out that these tiny spheres were lead bismuth that had oxides on the surface, but the oxides were only, I mean, the layer was maybe 10 atoms thick. It was kind of nuts. That we're talking about like 10 atoms thick. So meaning like, tens or 100 nanometers of oxide material stabilizing these droplets. And one of the ways that I figured that out, though, and they were running the temperature was around 500 Fahrenheit. So that's about 250-ish Celsius. And the melting point of lead oxide, for instance, I remember, was 888, just straight eights degrees Celsius. I'm like, yeah, you're just not hot enough to melt that thing. But that's one of the ways that I was able to argue. I'm like, look, you're going from metallic to an ionic bond, and ionic bonds have very high melting points. So yeah, there are lots of practical applications for this kind of stuff. So, but that's just one of them. But anyways, I guess we'll pick up here on Wednesday. But does anybody have any quick questions for the last minute of class? So as things stand, Monday is the we're going to be back. You'll find out when I do. Meaning we'll get an email from David Lasner, our president, telling us that classes may be canceled, but canceled, moved online. But I had the same information you do, so actually I find out the same time. So I don't know what's going to happen, but I'm prepped to go on Monday. So I'm good either way. So we'll see. All right, I'll stop recording.